Hi, Chem 101 students, and welcome to the last lecture of week 12. It's matter organization. So now we're going to use what we know about covalent and ionic bonding and also intermolecular forces to talk about the way in which all matter is structured. And we'll go into a little bit more detail about basically the chemical bonds versus intermolecular forces, their relative strengths, and also the effect that has on various properties of the substances, including their solubility in other substances. So first of all, I want to contrast the difference between chemical bonds versus intermolecular forces. And this is a slide I had shown earlier when I wanted to generally talk about bonding, but we hadn't talked about intermolecular forces yet, so I wanted to talk about the relative strengths of ionic versus covalent bonds. And we talked a little bit about metallic bonding. I'm going to go into a little bit more detail on that. But it's important to note that chemical bonds are much stronger than intermolecular forces or attractions between molecules. The strongest attractions that exist in matter are the attractions between ions. And remember, all these attractions are due to electrostatic attractions between positive things, positive electrical charge, and negative electrical charge. So it makes sense that ionic bonds are the strongest of attractions between chemical species. It's because ionic compounds contain fully positive particles, positive ions, and fully negative particles, the negative ions. And so those have an extremely strong attraction to each other, relatively speaking, when it comes to attractions between, these microscopic, submicroscopic particles we're talking about. And that attraction, that force of attraction, can be measured in terms of energy. So this energy is the energy that would be required to rip a mole of these ions apart from one another. And for ionic bonds, that energy ranges anywhere from 400 kilojoules per mole up to 4,000. So on average, ionic bonds are the strongest types of bonds, strongest type of attractions between chemical particles that exist. And covalent bonds are also quite strong. These are the attractions in between atoms due to shared electrons and making a covalent bond. The energy required to rip apart a covalent bond for a mole of molecules would be anywhere between 150 kilojoules to 1100 kilojoules per mole. So you can see that covalent bonds are on average weaker than ionic bonds, but there is some overlap there. Some ionic bonds are on the weaker side, some covalent bonds can be on the stronger side, but on average covalent bonds are weaker than ionic bonds, which makes sense because you have a fully positive and a fully negative thing attracting each other in the ionic bond, and here it's just electrons between atoms kind of shared, helping to glue them together. Now, metallic bonds are on average the weakest, although they can be quite strong. Metallic bonds are different from ionic and covalent bonds. So you may recall ionic bonds generally occur between metal and non-metal atoms, with some exceptions. Covalent bonds occur between non-metal atoms. Metallic bonds occur between metal atoms. And metallic bonds are very different than ionic bonds and covalent bonds. Metallic bonds remember what makes a metal atom different from a non-metal atom. Non-metal atoms have a much stronger grip on their electrons. Metal atoms have a very weak grip on their electrons. And the result is when you put a bunch of metal atoms together, their electrons are not held to any one particular metal nucleus. And so the electrons can jump from nucleus to nucleus to nucleus. And it's this movement of electrons that gives metals the properties that they have. Number one is metals can, for example, conduct electricity. This is due to these so-called delocalized electrons. Electricity is just electrons moving through like a metal wire or some conductive material. And what makes a conductive material conductive, like metals, is the fact that it's not holding on to the electrons very tightly to any one particular atom. So those electrons can jump from atom to atom to atom, and they can move from the power plant all the way to your house, and you can plug in your phone, and those electrons are forced in to your phone's battery, which pushes a chemical reaction backwards so they can store that separated charge, so later the electrons can move in the other direction and power your phone. Also, metals, you can unlike ionic compounds, like a block of salt, for example, if you hit it with a hammer, it will break apart because you're ripping apart these attractions between these ions on a microscopic level. With a metal, when you smack it with a hammer, instead it will flatten out and deform, and it's because there's no tight bond here between one negative ion, one positive ion, that when you break it apart, it cracks the thing. Here, these atoms are all sitting next to each other with a kind of mushy moving electrons that can move around. And so when you smash it, you push the nuclei around, but the electrons can move to accommodate that. And so you get properties of metal, like you can smash it and deform it. They can conduct electricity, and this is all due to the fact that the electrons are delocalized and very mobile. It also results in slightly weaker attractive forces compared to a covalent bonds. Now, comparatively speaking, non-bonding forces or intermolecular forces are on average weaker, but they can be quite strong. Now, some of these forces we don't talk about directly, like the attraction between an ion and a polar molecule. This is pretty strong. The strongest intermolecular force that we talked about between molecules of the same type is hydrogen bonding. And so hydrogen bonding occurs when you have a very polar bond with a hydrogen attached to a high electronegative atom such as nitrogen, oxygen, or fluorine. Notice this is the strongest intermolecular force that we discussed, but its energy is only 10 to 40 kilojoules per mole. That is much, much smaller than any bonding force. And so that's why you're going to see that molecular compounds that are their forces that hold them together are intermolecular forces that hold the molecules together. Those tend to be a lot of times solid liquids or gases, because their attractive forces are so much weaker than are the attractions between ions, for example. The attractions between molecules, intermolecular forces, are weaker than any of these bonding forces. But hydrogen bond are by far, by quite a margin, the strongest intermolecular force. Next are dipole-dipole forces. Remember, hydrogen bond is just a special case of a dipole-dipole force, attraction between polar molecules. So this is an attraction between polar molecules or molecules with a dipole. Dipole-dipole forces are strong as well. Hydrogen bondings is extra strong dipole force. Again, the name hydrogen bond is misleading because it's not a chemical bond. It's a non-bonding force. It's an intermolecular force, attraction between molecules. Hydrogen bonds are just an extra strong type of dipole-dipole force. We also didn't discuss ion-induced dipole. So if you got a nonpolar molecule next to an ion, it can attract some of the electrons, for example, this positive ion. This would be between ions and nonpolar molecules, but it wouldn't happen within, a pure nonpolar substance, so I didn't discuss it. There's also a dipole-induced dipole, which is a nonpolar molecule having a dipole induced by a polar molecule. Again, this happens in mixtures. So what we focused on was for pure substances. And so for pure substances, you can have molecules with hydrogen bonding to each other, dipole forces, or between two nonpolar molecules, the predominant intermolecular force would be London dispersion forces. And these, as you can see, they're on the low end, they are much, much weaker than any of the other forces. But look at on the high end. They can be almost as strong as hydrogen bonding on the high end, but these are only for very, very large molecules. Remember, London dispersion forces get bigger as molecules get bigger. And so London dispersion forces can be quite large for large molecules. But for molecules of similar size, hydrogen bond and dipole forces are much, much stronger than London dispersion forces. So what does this mean for the way matter is organized? First, let's talk about elements. Okay, so elements can either come in the form of atomic individual atoms, or they can come in the form of molecules such as N2 and O2. So for nonmetal atoms that exist as atoms, these generally include the noble gases, because the noble gases, as you can see from the periodic table, they have 8 valence electrons, so they don't have a energetic incentive to bond. So they tend to stay as individual atoms. And so when nonmetal atoms are atomic, like the noble gases, they are gases. They have very weak London dispersion forces because, as I told you, London dispersion forces get bigger for bigger molecules. But if you have individual atoms, their London dispersion forces are quite small. And so they are all gases at room temperature, very low boiling points. Also, in metals, like pure iron, silver, or gold, these have individual atoms as well. However, their electrons are delocalized because they're metals. Another way this is described is a nuclei in a sea of electrons, because the electrons can flow and move like water. And so we have nuclei, but the electrons are delocalized and they can move around very easily. And these are referred to as metallic forces. So these are bonding forces, metallic bonds. And so metals tend to be solids at room temperature because the metallic forces are bonding forces. All bonding forces are quite strong, and so that holds these metal atoms together quite strongly. Matter can also be arranged in molecules. So in terms of molecules, we have two big types, either polar molecules or non-polar molecules. Remember, molecules are made by covalent bonds between atoms, bonds between nonmetal atoms. So if we have water, for example, water is a very polar molecule. It has hydrogen bonding forces because it has hydrogen bonded to oxygen. And the result is that it has quite strong attractive forces. Hydrogen bonding forces are quite strong. They're an extra strong type of dipole-dipole force. And so the result is that water molecules are liquid. Water is liquid at room temperature due to these relatively strong attractions between water molecules. Now, sucrose, table sugar, also has hydrogen bonding forces. Look at all the oxygen-hydrogen bonds. Oxygen bonded to hydrogen, oxygen bonded to hydrogen, oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. It has so many oxygen-hydrogen bonds that sugar has extremely strong hydrogen bonding forces. And so the result is that it's solid at room temperature. Also, it's a relatively large molecule, so its London dispersion forces are quite big too. And so the result is that these tend to make solids and liquids, these polar molecules. Water, the reason why water is not a solid is because, although it has strong covalent bonds within the molecule, the attractions between the molecules are just relatively weak intermolecular forces. They aren't bonding forces, even though they're called hydrogen bonds. They're just an extra strong type of intermolecular force. And so that causes them to be liquid, not a gas, due to the fact that they're polar and they have these relatively strong attractive intermolecular forces. Now, some other molecules are nonpolar. For example, nitrogen is nonpolar, so that's what constitutes most of the air. Nitrogen is an element that's in a molecule. And then this is a big hydrocarbon molecule. So the hydrocarbon molecule is actually very large. If you have a hydrocarbon molecule with like 20 carbons and 40-something hydrogens, this is because of the large molecule, it's going to have relatively strong London dispersion forces. So you can see that for a small molecule like nitrogen, the London dispersion forces are very weak. And so it's a gas at room temperature. It has a very low boiling point. But for a very large nonpolar molecule, this is a nonpolar molecule because it only has carbon-hydrogen bonds, which are nonpolar. The London dispersion forces can get quite large, and so you end up with a solid. This is what would compose like Vaseline or petroleum jelly. It's solid, but it's also a goopy solid, right? So you can tell that the attractive forces, although strong enough to make it a solid, are still relatively weak relative to something that's very hard, for example. So the state For state for a nonpolar molecule depend on the size of the molecule. Nitrogen and methane, for example, are gases because they're nonpolar and very small molecules. But if you have a very large molecule, like in the petroleum jelly, they can be solids as well. If the London dispersion forces will get bigger for a larger molecule. That says molecule, which bothers me. I need to fix that. Molecule. Finally, there are other ways of bonding. We haven't talked about this way, but some nonmetal atoms bond in what's known as a covalent network. So although most nonmetal atoms all nonmetal atoms make covalent bonds, but most of them make molecules. But some nonmetal atoms, sometimes they bond in such a way that they don't make molecules. They make bonds one to another in this large network of bonds, covalent bonds called the covalent network. An example of that is diamond. Diamond is made all of carbon atoms, and those carbon atoms are all in bonds in a tetrahedral arrangement, but each carbon atom is bonded to 4 other carbon atoms in a tetrahedral arrangement, making what looks like, you can see, a very rigid structure. If you built a building in this way, it would be very strong. And likewise, diamond is a very strong material. It's the hardest known material, and it's due to this very, very tough covalent network structure that it has. Sand is also a covalent network. It's composed of silicon and oxygen, and this is bonded in a covalent network as well, where silicon is bonded to oxygen, bonded to silicon, bonded to oxygen, and you get this broad network of covalent bonds. And so because these aren't composed of molecules, they're all their forces between their atoms are strong covalent bonding forces. And so that's why these end up as tough materials with high melting points. It's because they don't have molecules, so their attraction isn't just intermolecular forces, it's strong covalent bonds between the atoms. So finally, we have ionic bonding. So again, ionic compounds, they don't have molecules, they have ions that are positive and negative. Those ions have very, very strong attractive forces. So that's why almost any ionic compound you see will be a solid at room temperature. It will have a high melting point because ionic bonds are the strongest of forces, and these aren't molecules. There aren't weak intermolecular forces holding the molecules together. Instead, all the atoms are stuck together, positive atoms to negative atoms, in a very tough type of structure. And so they tend to be solid. So sodium chloride, for example, sodium chloride actually has a low enough melting point that you could melt it with a Bunsen burner, because it's only positive 1 ions attracting negative 1 ions. So in terms of ionic bonding, it's on the weaker side, but it's still much, much stronger than any intermolecular force. So all ionic compounds generally are solids at room temperature. This is calcium carbonate, which is chalk, also solid at room temperature. Ionic compounds are solid at room temperature due to their very strong ionic bonds that stick all of their ions together in giant, tough chunks. So that is the way matter is arranged. And so now you have an explanation. Why are ionic compounds solid? Due to their very strong ionic bonding forces. Why are sand and diamond tough solids? It's because they're not made of molecules. They're covalent compounds, but they're covalent networks that are not molecules. And then why is water liquid and sugar solid? It's because of their relatively strong intermolecular forces. They are covalent molecular compounds, but they have relatively strong intermolecular forces, whereas nonpolar molecules tend to have weaker intermolecular forces, but those intermolecular forces can get larger if the molecules are large. And so that explains all the matter that you observe around you. It's due to these bonding and non-bonding forces that cause the particles that make these compounds up, or these elements up, to stick in certain ways, and that give them their physical properties that they have. Now, also related to the physical properties are phase changes. So we talked about melting points and boiling points. the temperatures at which the substance would change from one phase into another. There are names for the changes in states or changes in phases. You ought to know these and the relative energy. So to turn a liquid into a solid, you have to put in energy. So that's why I say the enthalpy or the heat energy of the system is higher. To melt a solid, like let's say you have ice, you want to melt it. If you heat it up, it will melt faster and more easily. Melting is also called fusion. The opposite, liquid going to a solid, is called freezing. And then from liquid going to gas, again, you have to put in energy. Like if you want to boil water, energy goes in. It's endothermic, as we say, putting in energy. So if you're going up the scale here, it's endothermic. You have to put in energy. Going from liquid to gas is called vaporization. They have to put energy in. Going from gas to liquid, that's called condensation. That happens when energy is removed. So you make it colder, basically. Going from liquid to solid, that's called freezing, as I mentioned before. You're probably most familiar with that with water. If you want to freeze water, you take energy out. You make it colder. And then finally, it is possible for substances to go straight between solid and gas. The most common example of this is dry ice or solid carbon dioxide, which goes at atmospheric pressure straight from solid to gas. Going from solid to gas is called sublimation, and going from gas to solid is called deposition. And heat energy or enthalpy is required to disrupt the intermolecular forces. So when you add in energy, you're causing the molecules, you're raising the temperature, you're causing the molecules to move faster and faster. And by putting this energy in, you can disrupt the forces, and they can move, the molecules can move past each other and whiz by each other and move more freely because they're jiggling and wiggling and moving faster. We have names for the energy that's required to initiate a phase change or to cause a phase change to happen. The energy required to convert 1 mole of a substance from a solid to a liquid is called the enthalpy of fusion, or fusion, the other name for melting. And then the energy required to convert 1 mole of a substance from liquid to gas is called the enthalpy of vaporization. And your textbook does some calculations with enthalpy and fusion and enthalpy of vaporization. I'm not going to go into too much detail on those calculations. I do expect you to be familiar with this terminology, though. Finally, in terms of solubility, we talked about the solubility of ionic compounds previously, and I gave you some solubility rules. I'm going to put these in here as well and briefly review them. But I'd like to talk about the solubility of molecular compounds, because we haven't talked about that yet, because to know whether a molecular compound is soluble in water, we need to know if it's polar or not. We call a substance dissolve into another substance, we call that a solution. We're going to be talking about solutions in the next chapter, but just as an introduction here to the terminology, the solvent is the major component of solution. For example, in salt water, it's the water. The solute is the minor component in the solution. Again, for salt water, that would be the salt. The salt dissolves in the water. The solubility is the amount of a substance that will dissolve in another. And when a substance dissolves, it's present as individual molecules or atoms or ions in the case of an ionic compound. So what about dissolving in water? So what's going to mix with water? Water is a very polar molecule. Other polar molecules can mix with water because these polar molecules will have attractions to each other, dipole-dipole attraction. So we saw that sugar, for example, has lots of hydrogen bonding forces. Water also has hydrogen bonding forces. So sugar mixes very well in water because they have a strong attraction to each other due to their polar nature of both their molecules. In general, compounds that have similar polarities and intermolecular forces will mix the best. This is often summarized as like dissolves like. So polar compounds will mix with other polar compounds. Nonpolar compounds will mix with other nonpolar compounds. But polar and nonpolar don't mix very well. Like, for example, oil and water. We know those don't mix. It's because oil, as we're going to see when we talk about biomolecules, vegetable oil, for example, is nonpolar. Or hydrocarbons like gasoline, these are nonpolar. But water is polar, so they don't mix very well. So for ionic compounds, to determine the solubility of ionic compounds, we use the ionic solubility rules, which we talked about earlier. And so now I'm going to give you mixtures of ionic and covalent compounds and ask you which of these are soluble in water. And before you can decide, you have to note whether the compound is ionic or if it's covalent. If it's covalent, you have to decide if it's polar or not, which is a lot harder than if it's ionic. You just go to the ionic solubility rules and use those to determine if it's soluble or not. And as I said, in solution, these substances exist as individual molecules or ions. That's why when you put sugar in water, for example, you don't see the sugar anymore after it's dissolved because individual molecules are too small to scatter the light. Additionally, if you put salt in water and dissolve the salt in water, the individual ions separate in the water, as we've discussed before. The positive ions are hydrated, and now I can talk a little bit about why that is. We already know now water is a polar molecule. The oxygen side of the water molecule is partially negative, and the hydrogen side is partially positive. So the negative side of the water molecules is attracted to the positive ions. Likewise, the partially positive side of the water molecules is attracted to the negative ions, which helps to separate the ionic compound and keep the ions separated in water when it's dissolved. This is referred to as solvation or hydration of the ionic compound. Just a reminder, solubility rules, you've seen this in previous slides, but I thought you might need them again, so I put them in this set of slides as well. If you have group 1 ions in your ionic compound, it's soluble. Ammonium ions or acetate ions or nitrate ions, whenever you see these ions in an ionic compound, it's always soluble in water. Chlorides, bromides, and iodides are generally soluble with the exception of silver chloride, lead 2 chloride, and mercury 1 chloride. Sulfates are generally soluble with the exception of calcium sulfate, strontium sulfate, barium sulfate, and lead 2 sulfate. And carbonates and phosphates are generally insoluble unless they're combined with always soluble ions like group 1 positive ions or ammonium ion. And sulfides and hydroxides are generally not soluble unless they're combined with a group 1 ion or a group 2 ion in the case of sulfides, or calcium, strontium, and barium, which is also group 2 for hydroxide. So now the kind of question I can give you is like what I asked you before for ionic compounds, like which ionic compound is soluble in water, but now I can mix ionic compounds and covalent compounds, and you should be able to determine are these soluble in water. So the first thing when you look at these compounds is to ask, is this ionic or covalent? That's often the case for many of these compounds. Remember, the way ionic and covalent compounds work are very different, so a lot of the ways in which we approach them will be different. It's always good to ask yourself when you're thinking about a compound and trying to evaluate its properties, is it ionic or covalent? Because we treat them differently. They're very different. So here we see only nonmetal atoms, so the NH3 is a covalent compound. Here also hydrogen, carbon, oxygen, these are nonmetal atoms, so this is a covalent compound. And then here potassium is a metal, so this is an ionic compound. It also has the polyatomic ion phosphate you can see there. So for covalent compounds, it's actually a lot harder to determine if they're polar or not, because, or if they're soluble in water or not, because we have to figure out if they're polar or not. So here we have NH3, so we should draw its Lewis structure to determine if it's polar or not. We have 1 nitrogen and 3 hydrogens. The nitrogen is in group 5, so 5 valence electron, hydrogen group 1, 1 valence electron. So 1 nitrogen times 5 valence electrons, 3 hydrogens, each with 1 valence electron. So we have 5 valence electrons from the nitrogen 3 from the hydrogen, 3 times 1 for a total of 8. Covalence number for nitrogen is however many more it would need to have 8. That will be 3. And for hydrogen, it's however many more it would need to have 2, because hydrogen's special. So it's always 1 to the covalence. So we put nitrogen in the middle for the highest covalence number there on the skeleton, and we put the hydrogens around it. Then we've got 2 electrons left because we put 2, 4, 6 down. We have 8 total. We can't put them on the hydrogen because hydrogen's full with 2, so we put them on the nitrogen. So now this has a nitrogen hydrogen bond, and the electronegativity for nitrogen is 3.0. We can look at the electronegativity chart right here. 3.0, 2.2 for hydrogen. So 3.0 minus 2.2, that is 0.8. Very polar. Or you could just think this has a bond between nitrogen and hydrogen. This is going to have hydrogen bonding forces. We can also see that here in terms of shape, X is 3 atoms bonded to the nitrogen. E is 1 lone pair on the hydrogen. This is trigonal pyramidal. So we have polar bonds and an asymmetrical shape. So this molecule is polar. Its intermolecular forces are hydrogen bonding forces. And so because it is polar, and especially because it has hydrogen bonding, it is soluble in water. Because water is also polar, so it will mix with water. Okay, and then the next one is also covalent, so we have work to do to draw the Lewis structure. I'm going to do this one pretty quick because I did this, this is formaldehyde. I did it back last week when we did Lewis structures. And so I'll do it pretty quick. We have 1 carbon, 1 oxygen, 2 hydrogens. Carbon is group 4, oxygen is group 6, hydrogen is group 1. 4 valence electron from the carbon, 6 from the oxygen, and 2 times 1 for the hydrogen is 2, for a total of 12. Covalence number is 8 times 4 for carbon, or 8 minus 4 for carbon, 4. 8 minus 6 for oxygen, 2. And hydrogen is always 1. We put carbon in the middle. And I'm just going to draw a Lewis structure. It's a double bond to oxygen, 2 hydrogens. We did this back in chapter 17. So first, we should look and see if we have any polar bonds. We have a carbon-oxygen bond, and we have a carbon-hydrogen bond. And electronegativity for the carbon is 2.5, and for oxygen, it's 3.5. So the difference here, 3.5 minus 2.5, that is 1.0. And I got those just from here. 3.5 for oxygen, 2.5 for carbon. For hydrogen is 2.2. So 2.5 for carbon, 2.2 for hydrogen. So 2.5 minus 2.2, that's 0.3. So the carbon-oxygen bond is the polar bond. This is a polar bond here. Polar. This is a not polar bond here, but we only need one polar bond. So we have one polar bond. And our shape for our molecule here, I mean, regardless of the shape, you can probably tell this is going to be asymmetrical because there's a different atom on the other side. But we might as well figure out the shape. X here is 3 atoms bonded to the carbon, 1 oxygen, 2 hydrogens. E is 0. This is formaldehyde. It's actually the exact example that we have here. It's trigonal planar, and due to the fact that oxygen is different from the hydrogens, even though it's a symmetrical shape, so trigonal planar is a symmetrical shape, that it would only be symmetrical, trigonal, planar. It would only be symmetrical if the atoms all the way around were the same, but they're not. So this side of the molecule here, where the oxygen is going to be partially negative because it's going to be pulling electrons away from the carbon. And this area where the carbon is will be partially positive. This is going to be a polar molecule. It has a polar bond and it is asymmetrical. So it is a polar molecule. It doesn't have hydrogen bonding because it doesn't have an oxygen bonded to hydrogen or a nitrogen bonded to hydrogen. So remember, to have hydrogen bonding forces, it has to have hydrogen bonded to either nitrogen, oxygen, or fluorine, which it doesn't have here. So it's dipole-dipole forces. Still, it's polar. Because it's polar, it's going to be soluble in water. Probably not as soluble as the ammonia because it doesn't have the hydrogen bonding, the extra strong dipole, but still soluble in water. Finally, the last one's ionic. We just go to the ionic solubility rules. We can see that phosphates are generally soluble unless it's with one of the always soluble ions like potassium. Potassium is a group 1 ion, always soluble, so this is soluble in water. Notice that was a lot quicker. We just had to use the ionic solubility rules. And so now you can expect, if I ask you what's soluble in water, what's not, you can expect to see a mixture of ionic and covalent compounds. And this will become important too as we finally talk about solutions in the next chapter. I'll talk about why you might care about this kind of stuff if you're a nurse. A lot of health problems are related to substances that develop in the kidneys, for example, that are not soluble in water. Kidney stones are an example. All these things that are stones, and these are insoluble substances that collected in the body. So it's very important to understand what's going on with a kidney stone, for example. Why does this occur? Because we have an insoluble substance developing in the kidney. And so that's what we're leading into as we go into solutions next week and talk about some of the important issues with things that mix up, especially as they relate to the sciences and also to the health sciences. We'll have some applications with that. So thank you for joining me in these lectures this week. Good luck on your homework, and I will see you next time.